in chemical reactions, you're starting with the reactants and you end up with products. The atoms and electrons in the reactants rearrange themselves and create new materials, new chemicals in the form of products. On paper, the balanced chemical equation can show all of this perfectly, how 2 molecules of this and 1 molecule of that will form 3 molecules of this other thing. And that works on paper, but in practice and in a lab setting, it's a little difficult to do that. In a balanced chemical reaction, it's focusing on moles and the moles or molecules that undergo these reactions. But in a lab, it's incredibly difficult to actually measure down to the molecular level about how much exactly you would have in order to react perfectly. And that's where the concept of a limiting reactant comes in. A limiting reactant is the one of those reactants that dictates how the reaction happens or how far along the reaction can go. The limiting reactant is something that would be used up first, and the other reactant that's there would be left over. So when you're going through and looking at the limiting reactant, it's the reagent or that initial reactant that there is less of it there. It can perform fewer reactions for the limiting reactant than the excess one. And this experiment looks at how to determine the limiting reactant, both in theoretical ways and calculations to determine the limiting reactant based on the sheer number of moles that are available in a situation. And the experiment itself also looks at determining the limiting reactant based on experimental observations, looking to see, based on experiments, what is the limiting reactant. In a lab setting, the limiting reactant is something that controls when the reaction is finished. The limiting reactant is of multiple reactants, the one that will get used up first. And once it's used up and gone, the reaction can no longer progress because that reactant is now gone. All of the other reactants will still be there and remain in excess. And this experiment looks at preparing different combinations and trying to decide what is the limiting reactant and how much of it was there, how much of it, of the excess reactant, was left over. So in a chemical reaction, there are both products and reactants. And the reactant is the starting material, and this is where the limiting reactant would be. It's the materials that rearrange themselves to generate something else. And that something else is the product, the end result. Most times in chemical reactions, the reactants appear on the left and the products appear on the right with an arrow in between pointing to the direction, going from products, or I'm sorry, going from reactants to the products. Now, there are a lot of different types of reactions. Some can be one reactant just rearranging and going into one product, one reactant splitting apart into 2 products, 2 reactants combining into 1 product, or a number of different ways that these things can react. And in a lab setting, you can't get these amounts down to the actual molecule. You can only deal with what you have in front of you, and that's weighing things out on a scale or a balance, or looking at volumes and masses.
And it's very, very difficult to have them exact to match up with a perfectly balanced equation. So in these real world situations, there will always be something that's not quite enough. There's not quite enough of something to fully react with everything else, and that would be the limiting reactant. So in a balanced chemical equation, something like this, you have, in this example, calcium chloride reacting with 2 sodium hydroxides as the reactants to give 1 calcium hydroxide solid and 2 sodium chlorides. These are the products. In this balanced chemical equation, you have 1 mole of calcium chloride plus 2 moles of sodium hydroxide to give 1 mole of calcium hydroxide and 2 moles of sodium chloride. How that would look in terms of the actual mass is if exactly 110.98 grams of calcium chloride reacts with 79.99 grams of sodium hydroxide, that will give the products of exactly 74.09 grams of calcium hydroxide and 116.88 grams of sodium chloride. But weighing out these exact masses can be tricky because there can be variability. These are also based on truncated atomic weights. So the actual down to the molecule would be farther out and have a greater level of significance. So in labs, one of these is going to be limiting based on the actual amounts that you weigh out. And in these reactions, the limiting reagent or the limiting reactant is what is controlling the entire chemical reaction. Because whatever excess material might be there is not going to be involved in the reaction. Only what can react with the limiting reactant is what will generate the product. So when going through and looking at chemical equations and calculating final mass of product or final moles of either reactant product, it's all based on the limiting reactant because that is the one part of the reaction that is controlling the rest of the reaction. In sticking with the same reaction that we looked at a couple of slides ago, the reaction of calcium chloride and sodium hydroxide, a much more relevant thing in a lab setting would be to weigh out some amount. So if exactly 50 grams of each was weighed out and combined, what would be the amount of products that would be generated? And what would be the limiting reactant? And to determine the limiting reactant, you first have to see how many moles of material you have. Chemistry is performed in moles, but the actual action in lab is weighed out in grams. So there's always going to be this conversion between grams and moles. A good rule of thumb, if you're ever given anything in a question, in a problem in grams, convert that to moles because that is what's going to be used in any sort of chemical equations or any sort of chemistry. So first off, if we have 50 grams of both calcium chloride and sodium hydroxide, the first thing we're doing is figuring out how many moles this happens to be. So you're dividing the mass by the molecular weight, and that's going to give the amount of moles of each material. So in the case of calcium chloride, we have 0.4505 moles. And with sodium hydroxide, there is 1.250 moles. Many times, especially in general chemistry, you might not be dealing exactly with weighing out the material directly, but you might be dealing with solutions of materials. So they have a specific molarity, and you're measuring out the volumes instead of the mass. The molarity, again, is a concentration. It's the amount of moles that are present within 1 liter of the solution. So with the same example, if 250 milliliters of a 1.802 molar solution of calcium chloride was combined with 500 milliliters of a 2.500 molar sodium hydroxide solution, you still have to go about finding how many moles there are of each component. And to do that, you're looking at the molarity equation. Molarity equals moles over liters. So to find the number of moles, you will multiply both sides by liters, by the volume, and that will equal the number of moles. So the molarity times the volume in liters gives the number of moles. So when we multiply the 1.802 molarity times the 0.250 liters, remember this was milliliters and it needs to be converted to liters, so that would be divided by 1,000. And when we multiply these two together, we get the 0.4505 moles of calcium chloride. And likewise, we get the same, the moles of sodium hydroxide. So in lab settings and in problems, you can either be given the mass directly, and if you're given the mass directly in grams, you can convert that to moles just by using the molecular weight. Or you could be given solutions, and this is a concentration and a volume, and you can calculate the moles from that. Either way, you're looking to find how many moles of starting material do you have for all of the different reactants. Once you have the moles of the different reactants figured out, you can then go through and multiply these by the stoichiometry. That's the balanced equation. Looking at this balanced equation, 1 calcium chloride will generate 1 calcium hydroxide. The ratio between calcium chloride and calcium hydroxide is 1 to 1. So if you have this many moles of calcium chloride and the ratio is 1 over 1, you're multiplying it just by 1. And this would generate 0.4505 moles of calcium hydroxide. Again, because for every 1 mole of calcium chloride, it generates 1 mole of calcium hydroxide. So if you have 0.4505 moles of calcium chloride, that generates 0.4505 moles of calcium hydroxide. They're the same because it's 1 to 1. With the sodium hydroxide, however, the relationship is 2 to 1. It takes 2 sodium hydroxides to react and combine to make 1 calcium hydroxide. So in essence, you're multiplying by the ratio of 1 over 2, or dividing by 2. So if we have a starting number of moles of the sodium hydroxide, 1.250, that will give 1.25 divided by 2, that will give 0.625 moles of calcium hydroxide. So in each case, you can see what the maximum amount of calcium hydroxide to be produced would be. And in this situation, the calcium chloride produces less. This is the limiting reactant. So an amount of 50 grams of calcium chloride will produce 0.4505 grams of calcium hydroxide, where 50 grams of sodium hydroxide will produce 0.6250 moles of calcium hydroxide. This number is smaller than this number, and that's what dictates the limiting reactant. What is the reactant that will use up everything and fully react until it's gone first? What will generate really the least amount? Because in this case, there's enough calcium chloride to generate 0.4505 moles. And there's enough sodium hydroxide to generate 0.6250. The difference between them is going to be the moles of sodium hydroxide left over. So when you have the limiting reagent, there are a number of things you can determine after that. You can look at how much of the actual product will be formed. If you mix these things together, how much of the end material will actually be generated. That would also be considered the theoretical yield. You can see how much excess reactant remains. So if the limiting reactant is all used up, it's going to react with sodium hydroxide. But how much of that sodium hydroxide is left over? You can calculate that and figure out using the same method as before by multiplying these through by the different ratio. And you can figure out how much more of that limiting reactant can be added into that system. So if there was excess sodium hydroxide, how much calcium chloride can that excess sodium hydroxide react with? There are a lot of things that you can calculate once you have the limiting reactant.
When a reaction occurs, you're taking the reactants, rearranging those atoms and electrons, and creating the products. In this example, there is the two reactants of hydrochloric acid, HCl, and magnesium metal. And when these two things react, they form hydrogen gas and a solution of magnesium chloride. So by mixing these two together, the reaction can progress. And you can see that it's generating the hydrogen gas, it's bubbling, it also generates a lot of heat. And the limiting reactant is the initial reactant that's going to dictate when the reaction stops. When all of the limiting reagent is used up, the reaction can no longer continue because it's gone. That does not mean that everything is gone. There is still some of the other reactant left over, and that other reactant can continue to react if the limiting reagent was added back in. So when going through and calculating different things, if you were to do this based on numbers, numerical values, how many moles of hydrochloric acid was there to start, how many moles of magnesium was there to start, you can figure out what the limiting reagent is, how much of it was there, and how much excess or how much of the other thing was there as well. But experimentally, you can also do that. The reaction is now complete, everything is used up, the limiting reagent is gone. But if there's any excess material, it can still react if the limiting reagent is reintroduced. So if I split this up into two portions, if I add more hydrochloric acid, nothing happens. There is no further reaction. So that means that there is no magnesium left in this reaction mixture for the hydrochloric acid to react with. However, if I add a little more magnesium, the reaction continues on. That means that there was still hydrochloric acid remaining. Hydrochloric acid was in excess. So the limiting reagent in that first reaction in the larger beaker was the magnesium. The reagent in excess was the hydrochloric acid. And by knowing exactly how many moles of starting material you have, you can figure out how many moles of actual product you're generating, and therefore how many moles of excess reagent is still there after the reaction. And you can figure out in a lab setting how much more limiting reagent do you need to mix into there for absolutely everything to be fully reactant and the reaction to be completed.
So you can generate a lot of different numbers and calculations once you have that limiting reactant determined. So one of the things you can calculate is how much product is formed. What is the mass of that solid, this calcium hydroxide? How much of that will there be when you combine 50 grams of calcium chloride and 50 grams of sodium hydroxide? You're trying to figure out what is the mass of that solid. So once you have the limiting reactant, you can see how many moles of product it will form. So in this case, you have 0.4505 moles of calcium hydroxide. And then using the molecular mass, you can convert moles back into grams. So in this example, when you combine 50 grams of calcium chloride and 50 grams of sodium hydroxide, you will end up with a total product of 33.38 grams of calcium hydroxide as a solid product. The other thing you can do is how much of that excess reactant is remaining. So again, this is all based on the limiting reactant. That's the starting point for these calculations. You have to determine what is the limiting reactant first. So in this case, the limiting reactant was the calcium chloride. And there is 0.4505 moles of calcium chloride. When you multiply this out by the ratio, for every 1 mole of calcium chloride, it will react with 2 moles of sodium hydroxide. And you're trying to cancel out this moles of calcium chloride, so that's going on the bottom. So you're multiplying it by 2. So 0.4505 moles of calcium chloride will react with twice as much sodium hydroxide. So that will react with 0.9010 moles of sodium hydroxide. So when you take that, multiply it by the molecular weight, you get how many grams of the sodium hydroxide actually reacted. And you can take this then, if you start it with 50 grams total and 36.04 grams of sodium hydroxide reactant, then there is 13.69 grams of sodium hydroxide remaining that still can react, but it's leftovers. You can also do it just based on the moles. You had a if you already converted the 50 grams into moles, you had 1.250 moles of sodium hydroxide. and 0.9010 moles reacted. So you're left with 0.3490 moles of sodium hydroxide that is left over and can still react. And kind of more of the last step is how much more limiting reactant is needed. So how much excess or how much limiting reactant can this situation handle before everything is gone? So you're figuring out how much is left over. So this excess reactant. You have 0.3490 moles of excess sodium hydroxide. And for every 2 moles of sodium hydroxide, it reacts with 1 mole of calcium chloride. So now, again, to make sure that this sodium hydroxide is canceled out, you're dividing by 2. It's the same ratio, but you're going in the opposite way now. So you're dividing by 2 instead of multiplying. So it will take half as much calcium chloride to react with this. So overall, a total of 0.1745 moles of calcium chloride is needed to fully react with everything of that excess sodium hydroxide. And then if you take that and convert to a mass using the molecular weight, you see that 19.37 grams of calcium chloride is needed. So overall, this reaction would be perfectly balanced in theory if you had 50 grams of sodium hydroxide and reacted 50 plus 19.37 grams of calcium chloride. Then it will react in these same ratios. But weighing things out in a lab doesn't always fall to that exact measurement. And that's why the limiting reactant is something that plays a major role in determining how much of the actual product is formed and what you can do with the remaining reaction. So in the reaction itself, there was the calcium chloride and the sodium hydroxide that was giving way to calcium hydroxide and sodium chloride. You notice that all of these have had a phase on them. The calcium hydroxide ends up being a solid, but I listed all of the other samples as aqueous. That means dissolved in water. And when you're taking an ionic solid and you're dissolving it in water, it's breaking apart into the individual ions. So an aqueous solution of calcium chloride would break apart into 1 calcium ion and 2 chloride ions. 2 sodium hydroxide compounds would break apart into 2 sodium ions and 2 hydroxide ions. The calcium hydroxide, again, is just a solid, so that's still going to be a solid. It does not dissolve. And the sodium chloride will break apart into 2 sodium ions and 2 chloride ions. So when you look at this, you'll notice that these 2 sodium ions appear on both sides of the equation. And the 2 chloride ions also appear on both sides of the equation. This equation right here is the full ionic reaction. Every single ion is taken into account and written out. And when you're looking at these, when you find something that's on both the reactant side and the product side, there's no change in the amounts or anything, that is a spectator ion. It did not participate in the reaction at all. So these, in this case, chloride ions and sodium ions did nothing. They were spectators. They looked on as the calcium ion and the 2 hydroxide ions are the ones that actually reacted and formed the calcium hydroxide solid. So while this is the full ionic equation when everything is broken apart, the net ionic equation would be just the reactants. So in their ionic form, the net ionic equation would be calcium ion plus 2 hydroxide ions to give 1 calcium hydroxide solid. And in future experiments, we'll go over in more detail of breaking apart these full reactions into full ionic equations and then net ionic equations. But right now, we're looking at just what is a spectator and what is the actual reactant when we're looking at overall what ions are present in these solutions and which ones are actually forming a reaction. This limiting reactant experiment is broken apart into 3 separate portions. The first part is looking at an online simulation and counting molecules and trying to balance reactions and figuring out how much material would be left over. The second part is watching a video and looking at the reaction that's performed in the video and using the observations to determine what is the limiting reactant in each case, and then how much material is present or how much product is actually generated. And then the third portion of the experiment is an at-home experiment where you're going to be reacting just the simple baking soda and vinegar, but in specific ratios. And from those ratios, you're going to see what is the limiting reactant in each case. So in the first part of the experiment, you're looking at a simulation and you're going to be completing a limiting reactant game, and you're going to complete level 3. If you'd like to perform levels 1 and 2, you can, but it's not required. Just going through and finishing level 3, and you're going to take a screenshot of the final screen, including what your score was. In the game, you're going to be looking at 5 different reactions. And for those reactions, you're going to record what is the balanced chemical reaction, and that's just given in the simulation, and the number of moles of reactant and product that is given in the simulation. So in the final balanced game, you're going to be tallying up how many moles or molecules of each component you have, both products, reactants, and leftover material, and then converting that into grams for each case using the molecular weight. When you follow the link, you will be taken to the reactants, products, and leftovers simulation. In the simulation itself, you're going to be choosing the game option. When you choose level 3, it takes you to the simulation itself. In the report, you're going to be recording what is the balanced chemical equation, the number of reactants that are given. In this case, there are 4 moles of ammonia, NH3, and 7 moles of molecular oxygen, O2. Using the balanced chemical equation, you can determine how many products are formed based on the amount of starting material you have. In this example, there are 4 ammonia molecules, and 1 full reaction uses all 4 of the ammonia molecules. In a full reaction, it generates 4 nitrogen oxide compounds and 6 waters. At which point, all of the ammonia is used up. So there are 0 molecules of ammonia left over. The reaction also uses 5 molecules of oxygen, and there are a total of 7. This means that there will be 2 additional oxygen molecules left over. You will go through this simulation and take a screenshot of the final screen, being sure to include the overall score of the game. So when you have the screenshot, or when you have each one of these different reactions, you're going through and you're going to be recording what is that balanced equation. Again, that's given. And then you're recording the number of reactants, number of products, and number of leftovers involved in this setup. So in this example, 4 moles of ammonia, NH3, and 8 moles of nitrogen monoxide are reacted together, and that will generate 5 moles of nitrogen gas and 6 moles of water. In this case, the ammonia is the limiting reactant because it's all used up. And the nitrogen monoxide is the excess reagent, and there are 2 moles of this remaining. So on the report form, you're going to be recording what are the reactants, and so there are 4 moles of ammonia and a total of 8 moles of nitrogen monoxide. And using the molecular weights, you can determine what is the mass of these components. Over on the products side, there are 5 moles of nitrogen, 6 moles of water, 0 moles of ammonia, and 2 moles of nitrogen monoxide. And then all of these can also be converted into a mass using their individual molecular weights. One thing you can do if you wish is to make sure that these are all correct. The mass on this side should equal the mass on this side. So the mass of reactant should equal the mass of product. And again, this is including all of the leftover components and everything. Because since there is a conservation of mass, every atom and every molecule is accounted for in this reaction. Nothing is remaining because you're accounting for that here in these leftovers. And in this example here, both the products and reactant side each have a final mass, or a total mass of 308.2 grams. There's conservation of mass throughout the chemical reaction. The second part of the experiment is a video. So you'll be looking at an unknown file, which is posted on Blackboard. You can choose any of the unknown files. And in that unknown file is going to be a link to a video. And that video contains 2 reactions. The first reaction is just mixing 2 things together, and the identity of those solutions are given in the unknown file. When those 2 solutions are mixed together, a solid precipitate will form. That is passed through filter paper, and the filtrate, which is the liquid that goes through the filter paper, is collected and separated into 2 different parts. And to each one of those separate portions, more of the reactant is added. So you're going to be going through and using those observations to experimentally determine what is the limiting reactant. The second reaction in the video is specifically between calcium chloride and sodium hydroxide. And in this reaction, you're again going to go through and see what is the limiting reagent based upon the observations, but then also the unknown gives you what is the concentration of the original solutions. And from those concentrations and the overall volumes, you can determine not only what the limiting reactant is, but also how much of it is there and what is the final mass of the product of calcium hydroxide. What is the theoretical mass? And finally, what is the actual mass of solid that's caught on the filter paper that was floating around in the solution, and making sure to take into account the solubility of the different components or of the different products. So both of these reactions, the first reaction and second reaction, are precipitation reactions. And you've seen these before in videos or in lab, and that's where you have two liquids that are mixed together and they form a solid. That solid is dispersed throughout the liquid. There's still a lot of water there because that's the solvent, but these two solutions are mixed together and the product is a solid sample. Now this product or this solid is primarily formed from the solubility number. So thinking back to the solubility table, that value on a solubility table is the limit. So any amount above that number or above that concentration will precipitate and form a solid. But if the overall concentration is below that number, it would stay dissolved and not react because it would be below the solubility limit. And this plays a critical role in that last part of part B, where you're trying to figure out when you mix the calcium chloride and sodium hydroxide together, you can calculate first through observations what the limiting reactant is, and you could calculate the theoretical yield, but some of that will be dissolved based on the solubility of the product. So you have to subtract that amount from the theoretical mass to figure out how much material is actually there. What is the mass of the powder that's floating around in that liquid?
In part B of the experiment, you're focusing on precipitation reactions. And you have seen precipitation reactions in a number of the experiments before. And a precipitation reaction is where you have two completely clear liquids, and when you mix them together, it forms a solid. And this is not a full chunk of a solid. This is particulate that's dispersed through a solution. Now, anytime you really can't see through the solution, if a solution is cloudy, that is an indication that there is precipitate that is in that liquid. One good example that you've probably seen before is milk. Milk you cannot see through. It's very, very cloudy. And the reason for that is the small particles of protein and fat. That's a precipitate. It's a solid, and it's suspended throughout the liquid. So that is a precipitate. If you were to leave milk sit for a very long time, you would see it even start to settle. I would not recommend that. But in other reactions, you'll be able to see the precipitate settle out to the bottom initially before too long. And in this reaction, in part B, you're looking at a few different precipitation reactions, and you're going to be separating the precipitate, the solid material, from the liquid material using filter paper. In a lab setting, one of the very important techniques when dealing with precipitation or recrystallization reactions is how to filter off the solid and the liquid. And many times this is done through the use of filter paper, very similar to coffee filters at home. There are two basic types of filtration using filter paper: gravity filtration and vacuum filtration. In both instances, the filter paper is provided in circular sheets. The difference between the sheets and how fast the filtrate can pass through it depends on the pore size and the packing of the filter paper itself. How tightly woven are the individual fibers, and how thick is it? These two properties will dictate whether the liquid will pass through it very fast and leave behind some of the particulate matter that will go through, or will it pass very slow but make sure that all of the solid and all of the particulate matter is captured by the filter paper and left behind. In these two techniques, you can see the difference between gravity filtration and vacuum filtration. The more basic filtration technique with filter paper is gravity filtration. With gravity filtration, a larger circle of filter paper is folded in half into a semicircle, and then the semicircle is folded in half again. What this ends up making is two separate lobes which could be opened up into a paper funnel. This paper funnel is then placed into a regular funnel, and the solution that needs filtration is passed through it. It's called gravity filtration because the only means to draw the liquid through is by gravity. The liquid that passes through the filter paper into the container below is called the filtrate. There are different grades of filter paper, as I mentioned, and sometimes it is necessary for analytical and very accurate filtration to pass the filtrate through a number of different steps of filter paper. Typically, this is good for most types of preparatory techniques where you need to filter out large pieces or larger precipitates, and the filtrate below can then be analyzed. Likewise, the precipitate on top could also be analyzed, and in future laboratory courses, the precipitate on top may also need to be washed with water to make sure all of the liquid is gone and only the solid, the clean solid, remains on top. The second type of filtration using filter paper is through vacuum filtration. In vacuum filtration, the filter paper itself is generally smaller and not folded, and stays a whole circle. These circles of filter paper are then used with a special type of funnel called a Buchner funnel. This funnel has straight sides on it and acts like a container. Inside is filled with a number of small holes. This holds the filter paper so it doesn't pass all the way through. It's placed onto a container that is connected to a vacuum system. The circle of filter paper can then be placed inside, the vacuum system turned on, and the solution poured through. Vacuum filtration is a much faster form of filtration. However, the special use of the Buchner funnel and the capability of pulling a vacuum on a glass container such as this is required. In many types of lab settings, a vacuum filtration would be used to more accurately collect the solid, where the gravity filtration will be used more so to look at the filtrate or the liquid passing below. As with the gravity filtration, once the solution is passed all the way through and the precipitate is remaining on top of the filter paper, it can then still be washed to make sure that the precipitate is clean. After the filtration, all of the solid remains on the top, and you can turn off the vacuum system and take the filter paper out and analyze the solid product on top. Being able to filter and separate out the solid component from the liquid component is a very important lab technique that's useful both in general chemistry, organic chemistry, and in more advanced chemistry courses. In the second part of the experiment, you're shown the gravity filtration technique on two separate reactions. To the filtrate, which is the liquid that passes through the filter paper, two additional tests are performed. Each of the original reactants is added to separate portions of the filtrate solution. Whichever reactant causes a precipitation reaction in that second set of reactions on the filtrate, that would be an indication that it is a limiting reactant in the first setup.
So in these reactions, when you're going through and performing or watching these reactions, they're being filtered through filter paper. And you've probably seen filter paper and not even realized that that's what it is, but coffee filters. It is just a piece of paper, literally, where you can have a blend or a mixture of solid and liquid, and you pour it into this filter paper, and the filter paper keeps the solid up top, and the liquid or filtrate passes through the paper and pours out to the other side. And there are a few different types of filter papers depending on the thickness and the packing of the fiber of the paper. Smaller particles can pass through or not, and the time it takes can also change. And there are two primary ways to filter using filter paper. There is gravity filtration, and this is just where you have a piece of filter paper either cut out and rolled into a funnel, or kind of fold it in half, then fold it in half again, and that will make a little paper funnel. and that goes directly into a regular funnel, and you just pour your sample right through it. This one does usually take a little bit more time, as it's just passing through the filter based on gravity, but is probably the most simple way to filter something. The other option is through vacuum filtration. And if you move on to organic chemistry, when you're creating solid products in organic chemistry, especially in the lab, you would be using this type of filtration setup to isolate them. So in this setup, you would have a little disc of filter paper put inside a funnel that looks like this, called a Buchner funnel. And when you do that, the bottom portion, this bottom flask, is hooked up to a vacuum. And then it literally sucks all of the solution through that filter paper in a much faster way. And this way you can filter a larger amount of solution faster, but you do have to keep in mind that the filter paper can get a little clogged up, so you'd need to either have might need to filter it a couple of times through different levels of filter paper. But going through and filtering these things, you can separate a mixture or a blend of solid and liquid into the solid component, and you can go on and perform chemistry with that, and the liquid component or the filtrate, and you can go on and perform chemistry with that. So you have this blend of solid and liquid together initially, and the filter paper is able to very nicely separate it into both of the different components. So in the video experiment, or in this reaction, you're taking the filtrate, that solution that passes through the filter paper. And in this reaction, calcium chloride plus sodium hydroxide, giving calcium hydroxide and sodium chloride. The calcium hydroxide is solid, so that is going to be captured by the filter paper. But any of the sodium chloride ions and any unreacted reactant will also be present in the filter paper, in the filtrate. It will pass through the filter paper. And what you're going to be doing, or what's being done in the video, is taking that filtrate, that liquid, and separating it into two different portions. And to each of these two portions, you're going to be adding one of the reactant. So in this setup here on the slide, if you have some of the filtrate and you add additional sodium hydroxide and nothing happens, that means that there is no calcium chloride in there for the sodium hydroxide to react with. If you add additional calcium chloride and there is a precipitation reaction, that means that there were already excess sodium hydroxide ions within that liquid. So when you added excess or extra calcium chloride, there was a precipitation reaction. So you can conclude from these sets of reactions what is the initial limiting reagent when you mix them together in the first place. Whichever one forms the precipitate in the second reaction step, that is going to be the limiting reagent in the first case. So in a sample like this, if the addition of calcium chloride causes a precipitate, that means in that very first reaction, when you mix both solutions together and it formed the solid initially, the calcium chloride was the limiting reactant. If the sodium hydroxide is the one that forms the precipitate, that means that the sodium hydroxide is the limiting reactant. So it's whichever one gets depleted first, and is the limiting reactant. And the excess, the extra reactant, those are still ions, and they're able to pass through the filter paper and still be present in that filtrate, in that liquid. And so if you end up adding additional limiting reactant, you'll see a further reaction, and you can figure out, based on those two separate reactions, what is the overall limiting reagent. That would be a qualitative observation. You're just figuring out what is the limiting reagent. And in that second reaction, the one specifically with calcium chloride and sodium hydroxide, you're getting a number. And that would be a quantitative analysis where you're looking at the amount, the specific amount. But overall, you're determining what is the limiting reagent for both of those different reactions. And then in the second one, what is the theoretical yield? How much of the calcium hydroxide is actually created? And to do that, you need to figure out how much limiting reagent is there in the first place. The last part of the experiment, or part C, is a home experiment. And you're mixing together baking soda and vinegar. And you've probably done this as a kid. You mix baking soda and vinegar and it makes the little volcano. Same reaction. So you're taking baking soda, or sodium bicarbonate, and reacting that with vinegar, which is acetic acid. The overall reaction for this produces water, carbon dioxide, and sodium acetate, which will be aqueous and dissolved in its ions. Now, this reaction does not produce a precipitate. This reaction produces carbon dioxide gas. So you should be able to visually see the reaction going on as it bubbles. So you're going to do this kind of the same thing that was in part B, but you'll do this at home, and instead of forming a precipitate and having that be the observation that a reaction occurred, this reaction forms a gas. And if the reaction bubbles, that is the indication that a reaction happened. So you're first going to prepare 1 teaspoon of baking soda and dissolve that in 7 tablespoons of water. That will take a few minutes or a couple minutes or so to dissolve. And then you're going to be reacting some of that solution with vinegar in 2 separate experiments. And in each case, you're going to be determining what is the limiting reactant in both of those situations.
The third part of the experiment is a home experiment where you're going to be mixing a couple of things at home that you've probably done in the past. You're going to be reacting baking soda and vinegar. And the reaction between these is sodium bicarbonate and acetic acid. And the products are carbon dioxide, water, and a solution of sodium acetate. So the first thing you're going to be doing in the reaction is preparing that solution of baking soda. You're going to be preparing 1 teaspoon of baking soda powder and 7 tablespoons of water. And when you have that prepared, you're going to be taking exact volumes, either teaspoons, tablespoons, of the baking soda solution and vinegar and reacting them together. The exact amount that you're going to be reacting is given in the unknown file. And when you take these together, you're going to be mixing some baking soda water or baking soda solution and some vinegar, and that will cause the reaction. And you've seen this reaction before. It's the reaction of baking soda and vinegar. When the reaction is complete, you're going to be taking 2 smaller containers and pouring some of that reaction mixture into each of them. And just like was shown earlier with the magnesium and hydrochloric acid example, you're going to take your solutions and to one side add a little bit more vinegar. Nothing really happens. And to the other side, you're going to add some solid baking soda. And when you do that, you'll see, in this example, I'm seeing the reaction happen. There's more carbon dioxide released. So in this setup, when I just randomly mixed an amount of baking soda solution and vinegar, by doing this secondary test, I can see that the baking soda was the limiting reactant, and I can look at that experimentally. In the reaction setup that you're going to be performing at home, again, you're going to be preparing your own baking soda solution, and from that solution, you can determine a molarity, and from the volumes you use, you can determine moles. And from the vinegar itself, you can determine the molarity of that solution. Vinegar is typically 5% acid, and that 5% can be converted into a molarity. 5% means 0.05 milligrams per milliliter. And that, now that you have an amount over a volume, you can convert that to a molarity. And using the amounts that you're given or the amounts that you're asked to do in the unknown file, either 2 teaspoons of baking soda solution, 1 teaspoon of vinegar, vice versa, you're going to be doing 2 different combinations of your baking soda solution and vinegar. Looking at that reaction and then performing the secondary reactions to see in that particular combination what is the limiting reactant.
So just like part B, you're separating these, the final product into 2 portions and then adding additional reactant to each of them to figure out what was the limiting reactant initially. So in the first initial reaction, you have some baking soda, you have some vinegar, and you react them. And that will make carbon dioxide gas, so that will bubble away, and that's your visual cue that the reaction is happening. And it will make some water and sodium acetate. But there can be excess either baking soda or vinegar present in that solution as well. So when you have that, your product solution, there's again the product, the water and sodium acetate, and any unreacted material. You're separating that into 2 components. And to the first portion of that, you're adding excess baking soda. And in the second portion, you're adding excess vinegar. Now, if you add excess baking soda and nothing happens, that means that there was no vinegar left in the container to react with that baking soda. So it's not the limiting reactant. If you add excess vinegar and it does form a reaction, you see the carbon dioxide bubbling again, that means that the vinegar initially was the limiting reagent. There was not enough vinegar initially to react with all of the baking soda. So when you mix these two together, again, you see the reaction taking place. The same would be true in the opposite way. If the vinegar does nothing, then that's not the limiting reagent. If the baking soda does something, then it was the limiting reagent. And you're going to be doing two reactions of this at home. So you're going to prepare the baking soda solution just once, and then you're going to mix that with vinegar in two different portions, two different ratios. And those ratios are given in your unknown file. And that way, you're going to see which reactions have limiting reagents, both in the first reaction or the second reaction. Overall, you're looking to see at the number of molecules that a reaction can react with, and looking at leftover molecules or excess reagent. You're looking to interpret individual observations to determine experimentally what the limiting reactant could be, both in parts B and C, looking at different types of observations, looking at either precipitate formation or the formation of a gas as indicators of a reaction. And you're also going to use the concentrations and the volumes given to figure out what is the actual mass, what is the theoretical yield in these different situations.
Overall, in this experiment, you're focusing on the limiting reactant of a particular reaction, and you're looking at that in a few different ways. You're first looking at them just based on counting the molecules and counting the moles. In the first part of the experiment, that reaction game, you're counting along to see how much material do you have to start with. So how many reactants do you have to start with? How many products that will form, and how many leftover initial material do you have? The second part of the reaction is that video, looking at precipitation reactions and going through and experimentally determining what is the limiting reactant, as well as calculating the amount of limiting reactant and figuring out through calculations how a limiting reactant can be chosen, and seeing the overall theoretical yield of a reaction, which is based on the limiting reactant. That last part of the experiment is the home experiment, where you're mixing together different combinations of baking soda and vinegar and seeing through the chemistry what is the limiting reactant in each of those combinations, by doing it experimentally and then calculating the overall mass of carbon dioxide gas that can be generated in those different setups. So hopefully by the end of this experiment, you can see and get a better visualization on what the limiting reactant of a reaction is and how it plays a critical role in chemistry, and particular in laboratory reactions.